We are live. Is anyone about to come up with a question? All right. I believe we last left off with, I think we did the invariant, right? All right. And we've done the 11-foot car and the 10-foot garage.
Yes.
All right. Lorentz transformations. It's going to be an evening filled with fun. Lots of math, lots of letters all over the board. Perhaps not as many Greek letters as some of you would prefer, but you know what? We'll do what we can. Now, there are enough eccentricities in this that I will keep referring to my notes. All right. So I have two reference frames. You can think of this as Earth and rocket, or however you want to look at it, but it's just two different points of view. This is moving to the right at some speed v. In other words, I'll make that point positive. The velocity of s prime with respect to s is v. That's the shorthand notation for what I'm trying to convey here is that this s prime frame is moving at a speed v to the right. If we synchronize the clocks, so picture this rocket is zipping by Earth, and as soon as the rocket is right beside Earth, that they both start the timers. So the initial time is equal to the prime time, initial prime time, which is equal to 0. So we're saying basically we're allowed to synchronize the clocks. So at some time t, this s prime frame is moved a distance out of, well, v times t. So if I have something at this location here, then in s prime's frame, this is at some position x prime. So from this point of view, it's at some position x prime, and from s's point of view, it's some position x. So in Galilean relativity, x prime plus vt is equal to x. This is Galilean relativity. This is the type of stuff that we've basically been assuming pretty much since until last week. Or we can write it in terms of x prime is equal to x minus vt. And just to show that this is incompatible with special relativity, in special relativity, we did show that c squared t squared minus x squared is equal to some constant. No matter what reference frame you're in, this is one of the two invariants, the other invariant being the speed of light. So this would be equal to c squared t prime squared minus x prime squared. And in Galilean relativity, not only can we synchronize them, but they're always the same. So this becomes c squared t squared minus x squared. If Galilean relativity was compatible, this would become c squared t squared minus x minus vt squared. Well, those cancel out. So I'm left with negative x squared on the right, and on the left, negative of x squared minus 2x vt plus v squared t squared. for equals negative x squared plus 2x dt minus v squared t squared. My negative x squareds would cancel out. At this point, I can divide by vt. And what I ultimately end up with here, if I bring this over to the other side, I have that the speed times time, in other words, that distance right there, is equal to 2 times x. And that's not always going to be the case. So there's inherently an incompatibility with some of the stuff that we've done with the classical thinking and more the modern thinking. So there must be some relationship between x prime and x and t prime and t so that this does work, and that's what we're about to explore. We are deriving the Lorentz transformations. In post-production, we'll do zoom in. All right, we will start out with an assumption. I'm going to sort of hand wave through why this is a legitimate assumption, just because there are plenty of things to go over. I am going to assume that there's a linear relationship between x and x prime, as there is between t and t prime. So I'm going to say x prime, let's make sure I'm doing this the right direction. I am, is equal to some constant times x plus some other constant times t. And t prime is equal to a different constant times x plus a different constant times t. We are still going to synchronize it so that the initial times are still the same. So that oh, okay. I just did this 2 days ago. All right. So let's take a look at the origin right here. Or at the, actually at the origin right here. When x prime is 0, at that particular instant, then 0 is equal to a1x plus a2t. If this relationship is always true, it should be true for any specific instance. So we can come up with a relationship here, at least between a1 and a2. So negative a1x is equal to a2t. And I want to get this in terms of x. So x is negative a2 over a1 times t. Which is just equal to v times t. Because the origin in the prime frame is just the distance vt away from where it started. So we have that the speed, whatever my a1 and a2 are, we have a relationship here that the speed is equal to negative a2 over a1. So if I go back to my relationship here, I factor a1 out, I have x prime is equal to a1 x plus a2 over a1t. And so at least I've gotten rid of one unknown. So this is equal to a1 x minus vt. So we just have to figure out a1, and we've got one of the major Lorentz transformations. Questions up to here? So let's bring in our invariant. I am gonna stick to my notes, for some reason my notes, I flipped it around, it doesn't make a huge difference. I take all that and just flip sides. So, in other words, I have the x first. X prime is equal to c squared, t prime squared is equal to x squared minus c squared, t squared. I have a reduced formula here for x prime. So this is a1 x minus vt squared minus c squared times, it's not reduced yet, but it's all we have at the moment, b1x plus b2t squared is equal to x squared minus c squared t squared. So if there is a linear relationship here, then this must be true for all values for whatever appropriate values are for a1, b1, and b2. And so now we just go through the brute force of we're squaring binomials. So this is a1 squared times x squared minus 2x vt plus v squared t squared minus c squared times b1 squared x squared plus 2b1 b2 xt plus b2 squared t squared equals x squared minus c squared t squared. And if I don't make a careless error while doing this, I'm just going to be shocked. Loads of places to make a mistake. Go ahead and distribute the a1 squared to the c squared. So we get one giant long alphabet soup. X vt a1 squared plus v squared t squared a1 squared minus c squared b1 squared x squared minus b1 b2 c squared xt plus c squared b2 squared t squared is x squared minus c squared t squared. And it's obvious what the solution is. But for those of you who haven't quite caught up, I'm just basically killing time for people to catch up in writing, so. And for people to point out any careless errors I've made so far. Okay. So now I'm going to basically get the x squared terms together, get the x terms together, and then the non-x terms together. So I have an x squared term there, an x squared term there. I've got regular old x there, regular old x there, and then the two I haven't underlined are the non-x terms. So bringing these together, I get x squared times a1 squared. And I was actually taught how to make my letters. And somewhere along the line, I had to start writing in vertical surfaces. Minus c squared b1 squared plus x times negative 2 vt a1 squared minus 2b1 b2 c squared t plus, and then the other two terms, v squared t squared a1 squared plus c squared b2 squared t squared is equal to x squared minus c squared t squared.
I have a question.
Yes.
For the second line?
This?
No, the one above.
Oh.
So when you're distributing c squared, I think you're supposed to put a negative sign before the b squared t squared.
Over here? That should be a minus sign.
Yeah.
Which makes that a minus sign. Okay. Alright. I got my chaos error out of the way, I can write this. Alright, so I've got these two equations here, which I'm claiming are gonna be equal, that I can come up with some linear relationship between what's happening in the prime frame and what's happening in the non-prime frame. So therefore, if these are always true, then this must equal 1, because I have 1x squared here, I better have 1x squared over there. So I have a1 squared minus c squared b1 squared equals 1. I don't have an x term on the right, therefore this bit right here must equal
0.
So I have negative 2vt a1 squared minus 2b1 b2 c squared t equals 0. And this, what does that equal?
C squared, D squared.
Say it again?
C squared, T squared.
Darn close.
Or,
Yes.
yeah, negative.
So v squared t squared a1 squared minus c squared b2 squared t squared is negative c squared t squared. All right. Now let's do a little simplifying here, especially on that last one. Kind of liking that. All right, let's need some room over here, so let's get rid of this Galilean stuff. Okay, so that still holds, all right. So if I solve for B1 in that first equation over there, I have B1 equals, bring that over, so I have A1 squared minus 1 over C squared. That's B1 squared. That second equation, I want to solve for B2 squared. Or actually solve for B2. So I bring that, I get rid of my 2's. Get rid of T. And so this now becomes VA1 squared plus B1 B2 C squared equals 0. So B2 would be negative VA1 squared divided by B1 C squared. Wait a second. So I have A1 squared, B squared. Minus C squared. Oh. Not what I wanted to do. I wanted to take this one and solve for B2 squared. I had the audacity to write them down in a different order than I had them written down in my notes. So from the second equation, which reduces, we're down to V squared A1 squared minus C squared B2 squared equals negative C squared. We're going to treat that other one slightly differently. So we end up with B2 squared equals V squared A1 squared plus C squared divided by C squared, which is V squared over C squared A1 squared plus 1. And then the equation that I had manipulated, but then realized I didn't want to, if I solve for A1 squared no, that was a V, I was right the first time. A1 squared V equals negative B1, B2, C squared. And if I just square both sides, I get A1 to the fourth, V squared is equal to B1 squared, B2 squared, C squared. Now this last little bit right here where I squared both sides, because I have a value for B1 squared and B2 squared, I can just plug them straight in. And I get yet more letters jumbled together, but it does actually come out rather nicely. If you've been doing relativity long enough, or studying over the past week, you might have already guessed what A1's gonna be, but we're gonna show it. It's true. So A1 to the fourth, V squared equals B1 squared, which is A1 squared minus 1 over C squared, times B2 squared, which is V squared over C squared, A1 squared plus 1, times C squared. All right, there's a careless error that I made over here, because that's what I do. That should be C to the fourth. C to the fourth. If I distribute the C to the fourth